Hello, welcome to tutorial 19 in the practical RF design tutorial series. My name is Dr. Prakash Sangaran and I am a Keysight certified expert. In this tutorial, we will learn the complete design and optimization guide for a novel multiband planar inverted L antenna. This antenna is implemented on a rigid printed circuit board. This antenna covers 617 MHz to 960 MHz, 1.71 GHz to 2.2 GHz, and 2.3 GHz to 2.69 GHz. This antenna supports technologies such as 4G or LTE, 5G, Wi-Fi, Bluetooth, Zigbee, amateur radio 900 MHz and 2.3 GHz, UHF frequencies, LoRaWAN, Sigfox, RFID, TETRA radios, and satellite bands such as L band and S band. The flowchart above shows antenna design step. We will start our tutorial by giving an introduction to the antenna. The first step of designing an antenna is antenna selection. The next step is design the selected antenna. The third step is to optimize the antenna, followed by antenna EM simulation. Finally, the results of the antenna will be analyzed. This is a 4-part tutorial. In tutorial 19, we will cover antenna introduction. In tutorial 20, we will cover antenna selection, design and optimization part 1. In tutorial 21, we will cover antenna optimization part 2. In the last tutorial, tutorial 22, we will cover antenna optimization part 3, antenna EM simulation and results and analysis. Let's continue with tutorial 19. Figure 5.1 shows the basic radio architecture. The basic RF radio system contains baseband processor, up conversion mixer, down conversion mixer, voltage control oscillator or VCO, local oscillator or LO, or frequency generating unit or FGU, pre-driver, driver, final power amplifier, coupler, power controller, antenna switch, harmonic filter, antenna, pre-selector filter, low noise amplifier or LNA, and post-selector filter. Each radio component plays a unique and significant part in achieving the end goal of receiving and transmitting information wirelessly over a long distance. In figure 5.1, the antenna is the first component from the right of the radio system. The antenna is used to transmit and receive signals. The signal received by the antenna will be routed to the receiver section by the antenna switch. In the same way, the signal to be transmitted will be routed to the antenna via an antenna switch. Webster's dictionary defines an antenna as a metallic device, either a rod or wire, for radiating or receiving radio waves. The IEEE standard definition of term for antenna define antenna or aerial as means of radiating or receiving radio waves. The antenna is transitional structure between free space and guiding device. What does an antenna do? The antenna acts as a transducer that converts electromagnetic wave to electrical energy and vice versa. This process is bidirectional as shown in figure 5.2. If an alternating current is applied, the antenna will produce electromagnetic field surrounding the structure. When this electromagnetic wave hit a receiving antenna, they will induce a current on the antenna surface, which will then be converted to a message by receiving radio. Antenna types. In the previous tutorials, tutorial 15 to 18, a PIFA antenna design is presented. In those videos, antenna types are given in detail, so we will not repeat it here. Let's look at something far more interesting. One of the first questions that may be asked concerning antenna would be, how is the radiation is accomplished? In other words, how are the electromagnetic field generated by the source, contained and guided within the transmission line and antenna, and finally detached from the antenna to form a free space wave. Let's first examine some basic source of radiation. This theory is taken from the book titled Antenna Theory Analysis and Design by a famous author, Konstantin Balanis. Conducting wires are material whose prominent characteristic is motion of electric charges and the creation of current flow. We will be analyzing a conducting wire as shown in figure 5.3 to understand the radiation properties. There are some important variables we need to understand first before understanding the radiation. The first variable is QV, which is electric volume charge density. A is cross-sectional area, V is volume, Q is total charge, Vz is uniform velocity, Jz is current density, Js is wire surface density, Qs is surface charge density, Ql is charge per unit length, dVz over dt is acceleration of charge, L is wire length, Iz is current in the wire, and diz over dt is time varying current derivative. This equation is the basic relation between current and charge, and it also serves as the fundamental relation of electromagnetic radiation. It simply states that to create radiation, there must be time varying current or an acceleration or deceleration of charge. To create charge acceleration or deceleration, the wire must be curved, bent, discontinuous or terminated. Periodic charge acceleration or deceleration or time varying current is also created when charge is oscillating in a time harmonic motion. Therefore, if a charge is not moving, current is not created and there is no radiation. If the charge is moving with uniform velocity, there is no radiation if the wire is straight and infinite in extent. There is radiation if the wire is curved, bent, discontinuous, terminated or truncated as shown in this figure 5.4 here. If the charge is oscillating in time motion, it radiates even if the wire is straight. Let's try to understand the radiation mechanism from figure 5.4. When the wire is initially energized, the charges in the wire are set in motion by electrical lines of force created by the source. When the charges are accelerated in the source end of the wire and decelerated during reflection from its end, it is suggested that the radiated field are produced at the end and along the remaining part of the wire. Stronger radiation with a broader frequency spectrum occurs if the pulses are shorter or more compact duration, while continuous time harmonic oscillating charges produces ideally of single frequency determined by the frequency of oscillation. The acceleration of charges is accomplished by external sources in which forces set to charge in motion and produce associated field radiation. The deceleration of the charges at the end of the wire is accomplished by internal forces associated with induced field due to the buildup of charge concentration at the end of the wire. The internal forces received energy from the charge buildup as its velocity reduced to zero at the end of the wire. Therefore, charge acceleration due to exciting electric field and deceleration due to impedance discontinuities or smooth curve of the wire are mechanisms responsible for electromagnetic radiation. With this, tutorial 19 comes to an end. For inquiries, please email pragash@innovave.co or visit www.innovave.co.